All right, calculus kiddos, welcome back for hopefully our fifth and maybe final edition of Jensen Doing Calculus, at least on my YouTube stream. Hopefully you guys have been enjoying it, that it's been helpful and beneficial for you guys as far as learning that. And without further ado, I'm going to get into it today. So let me start here. We're doing problem B1. And so here's what we have. We have two different functions they've given us, and I want to talk about the scenario so that we understand what's going on here, because I think it helps a lot in the problem. So vehicles are arriving at a toll booth, okay? And so they gave us a function to represent that. They told us that we're going to call this function L of t. I'm imagining L for like the waiting in line, okay? But how much the line is building up. And L of t, they said, is twice differentiable, which will be valuable later. It's twice differentiable, and it's given by this table. So at any given time, in minutes, you can say how many cars are in line at this toll booth. So for example, at 30 minutes, there's 120 cars in line at the toll booth. Well, the reason that's important is because once we get to a toll booth, we don't just immediately blow through it. What we have to do is we have to wait for that line to get all the way till it's our turn to pay the toll. So they gave us a second function to model this, and the second function is our waiting time, or what we're going to call W of x, where W of x is the seconds that we're waiting once we get in line, and x is the number of vehicles. So obviously, what it's trying to show us is that if we get in line when there's only 10 vehicles in line, then our wait time is going to be pretty short. However, if we get in line at 30 minutes into this, when we started modeling this, and there's 120 cars in line ahead of us, our wait time is going to be a little bit longer. So we have two different functions modeling this, and then what I like to do is really understand what's going on first before I even read what they want me to do. It helps me at least gather what I'm trying to do for the problem. So let's get into part A now. Now I can say, okay, they want me to approximate the rate of change at t equals 80 minutes of the number of vehicles in line. So for this first one, what I'm thinking is, oh, they want me to just use the L of t function, and they want me to use it at t equals 80 minutes, approximate a rate of change of this one, okay, of the number of vehicles in line. So I know I'm using L of t. So for part A, I want the rate of change at t equals 80 minutes, and they said approximate. The reason we have to approximate is because to find an exact rate of change, we would need the derivative, and although L of t they told me is differentiable, from a table of values we can't find the derivative. So to find the rate of change then, if we can't find the derivative, we want then the slope of the tangent line, but that can't exist, so we're going to get the slope of a secant line. That will give us the rate of change. So our rate of change is the slope of the secant line, or that's f of b, like y2 minus y1, f of a, over b minus a, so y2 minus y1 over x2 minus x1. We're finding the slope of a secant line. Now, in previous problems that we normally see on the AP test, whatever time they give us for 80 minutes, usually they've given you 2 points of information that are both outside of 80 minutes, and they don't actually give you information at 80 minutes. So most often on a table like this, they would give us, like they would say, hey, find the rate of change at 85 minutes, and you'll notice then that 85 minutes would be exactly halfway between 80 and 90. In this exact problem, they didn't do that. They want the approximate rate of change at 80 minutes. Well, that means that this is going to be one of our points, most likely, and then we can use either the 60 point or the 90 point. Because they didn't give us information on either side and we're approximating, we actually get to choose, and all three options would be correct, meaning our 2 points can be these two, our 2 points that we could pick could be these two, or our 2 points could be these two, the ones outside. But these aren't equidistant away from 80. This is only 10 away, and this is, this is 20 away here, and this is 10 away. So I'm going to end up using these two as my points. And you may have done the problem slightly differently and still gotten a correct solution. So here we go. If I do that, if I'm using 80 and 90, then that's going to be the y value at 90, which is 0, minus the y value at 80, which is 60 vehicles. divided by b minus a. So that would be 90 minus 80. So essentially it's y2 minus y1 in the numerator and x2 minus x1. At this point here, on the AP test, this is all algebra, this isn't calculus, so we're going to tell you to stop here and put your units. For today, I'm going to end up solving it because some of you guys may want that. And I get negative 60 over positive 10, which is negative 6. And then we just need some sort of units here. Remember that this is the vehicles in line. And when we find a rate of change, it's taking the derivative with respect to time. So it's vehicles in line per minute. Okay, so it's vehicles per minute. Because L of t gives us the vehicles in line. When we take the derivative or find the rate of change, that is with respect to time. The time for the first section, the first equation was in minutes. Again, if you had chosen different points here, your answer would have looked slightly differently. And the way this was set up, that all three of those would be correct. Hopefully that makes sense, and we're done with part A, and we'll move on to part B. Okay, so we finished part A. We found our answer for the approximate rate of change at t equals 80 minutes of the number of vehicles in line. That was using our L of t function. And we used f of b minus f of a over b minus a. Now we go to part B. Part B says find the rate of change of the wait time, okay, the wait time, when 60 vehicles are lined up. Okay, so we have two different functions. Remember, L of t is the number of vehicles getting in line, where W of x is the waiting time once they're in line. So they want the wait time, so I know I'm going to be using my W of x function. Okay? And to find the rate of change, the exact rate of change, all we need is the derivative. That'll give me the instantaneous rate of change for that function. So I'm going to take the derivative of W of x, and then if I do that correctly, I'm going to put in 60 vehicles for x, and I will be able to get the instantaneous rate of change. So here we go. Remember W of x, they told me was equal to 30 sine of pi x divided by 180. Remember where W of x is representing the number of seconds that you're waiting, and x is the number of vehicles in line. So when we take the derivative, it's important to know that what we're taking the derivative of, okay? So here, if I just put in x, x is representing a number of vehicles in line. So if I said, hey, if there's 180 vehicles in line, what is my waiting time? W of x is my waiting time, okay? So my answer currently, this would be in seconds. However, I'm going to take the derivative with respect to x, okay? Well, the derivative with respect to x is the derivative in terms of vehicles, okay? So we're taking d dx, which is the derivative with respect to vehicles, because x is vehicles here. So as I take d dx of this whole thing, W of x equals 30 sine of pi x over 180. What I want to point out is that this units we can determine now is going to be seconds per vehicle, because we took the derivative not with respect to time, but with respect to x, and for this function, x is representing the number of vehicles. Hopefully that first part makes sense, because from here now, this is where we're going to just put our calculus skills to work. Here, this is going to give me W prime of x equals 30 is a constant, that's fine. Sine, I need to take the derivative of sine. Remember, sine is so happy, so when we take the derivative, it stays positive, it turns into positive cosine. Inside part, I'm going to have to apply the chain rule. So when I apply the chain rule, the first thing I do is I write the original times, chain rule says I need to take the derivative of the inside part. The derivative of pi x divided by 180 is this is just pi over 180 is a constant times x. So like if I took the derivative of 3x, the derivative of that would be 3. The derivative of pi x divided by 180 is just pi divided by 180. Okay? At this point now, this constant can go out front to kind of simplify that a little bit. So this is W prime of x equals 30 times pi is 30 pi divided by 180 times cosine of pi x divided by 180. 30 divided by 180, that's going to reduce to pi over 6. Pi over 6 times cosine of pi x over 180. So, here now, I am looking for the rate of change when 60 vehicles are lined up. Remember, 60 is our x. So we're going to find w prime of 60. Let me see if I can fit it in here. I'll change colors to black. Maybe that'll help it a little bit. So when I do that, I'm doing w prime of 60, which means I'm putting 60 into this equation. So it's pi over 6 times cosine of pi times 60 divided by 180. Okay. So that's putting in 60 into this function. So that's going to equal pi over 6 times cosine of, simplifying this, 60 divided by 180, that's going to just turn into pi over 3. We can't stop here because this is still like calculus-based work they want us to be able to know. So I need to figure out what cosine of pi over 3 is. Because it's open note on the AP test now, you could just go and look that one up on a unit circle if you don't want to rely on your left-hand rule knowledge. I'm going to use left-hand rule for me today. Pi over 3 is this value here. Remember, cosine is the x value at pi over 3, which would be positive 1/2. So I got pi over 6 times positive 1/2. And then when I multiply this gives me pi over 12. And they specifically asked me on this problem to indicate the units of measurement. Luckily, we've talked about this. W of x is representing seconds. And so w prime of x, when we take the derivative with respect to x, and x being vehicles, this is going to be seconds per vehicle. Okay, so seconds per vehicle. And that gives me my answer here for part B. So here we're on part C. Part C, here's what they've asked me to do. They've asked me to approximate this integral, the integral from 0 to 60 of L of t dt using the trapezoidal sum. So what I did is I said, okay, let me take L of t and let me graph this one. And then they've asked me for the integral L of t from 0 to 60 using a trapezoidal sum, which means I want essentially I want to make trapezoids to find the area under the curve just between 0 and 60. So right away what you can realize is that I graphed the entire graph, but I only need the graph up to 60 because that's where I'm going to stop. And I'm going to erase that part of the graph for part C so that I remember I'm stopping right here. To use a trapezoidal sum, there's some fancy formulas out there. However, the way that I like to do it, and my students kind of bore that with me, is I like to find the area of each individual trapezoid that I have and just add them all up. Okay, so I know that L of t, the integral from 0 to 60 of L of t dt using the trapezoidal sum, which is what they've asked me to do, is I got to decide how many trapezoids I'm going to use. I'm going to use 1, 2, 3, 4 trapezoids because I can make 4 trapezoids with the data given to me by the table. And they didn't tell me exactly how many trapezoids that they wanted me to use. So I'm going to assume they want me to use all these different values that I have from the given table. So that means I'm finding the area of trapezoid 1, area of trap 1, plus the area of trap 2, for trapezoid 2, plus the area of trapezoid 3, plus the area of trapezoid 4. Now remember, the way that these trapezoids are going to look here, that my trapezoid for the first one is this trapezoid right here. And for this trapezoid, we need to use the trapezoidal formula, which is 1/2 base 1 plus base 2 times h, times the height. Okay, so that's going to be, we're going to write this as 1/2 base 1 and base 2. So these are like trapezoids, but you'll notice they're trapezoids on their sides. So normally base 1 would be right here, this would be B1, and base 2 would be this piece right here, B2. So the base lengths end up being the y coordinates on the table. So my base 1 value ends up being just 10. Okay, so 10 is my base 1. plus my base 2 value is the y coordinate at 10, which is 50, times the height. Well, the height of my trapezoid is this delta x, or this whatever this distance is here. You'll notice because these are uneven, this height or this distance here is going to change for each trapezoid. And here in this case, this total distance is 10 because 10 minus 0 is 10. Maybe I'll do the heights in blue. Maybe that'll help. And I go to my second trapezoid. Again, it's the same formula for area of a trapezoid. 1/2 base 1 plus base 2. So base 1 is this height now for the second trapezoid, which is 50. Plus base 2, which is the height here at 30, and that's going to be 120. Times the height, and the height for trapezoidal 2. So this is T1. Height for T2. Base is 50, 120, and the height, or this length here, is the difference between 30 and 10, which 30 minus 10 is 20. Plus, I'm moving on to trapezoid 3. Trapezoid 3, again, I'm going here. This is my T3. And so I'm doing the height here at 30, which is 120, and the height at 45, which is 64. So it's 1/2. 120 plus 64 times the length here, or we're calling this the height, which is 45 minus 30. This piece here, that's going to be 15 because 45 minus 30 is 15. Plus, we need one more trapezoid, so I can write it below because I'm out of room here. Trapezoid 4, T4, and again, that's going to be 1/2. This height here, which at 45 is 64, plus at 60 it is 90, that's this length here, is 90, times this base length here. This length here is 60 minus 45, which ends up being 15. The beautiful part is that outside of the units on an AP calculus problem, we want you to stop here. Don't do any of the simplification because we don't need to. And if you do and you make a mistake, you get it wrong. The only reason we would ever want to simplify this any further is if we're going to use that number later on in the problem for some reason. Now, the only thing we have to put on here is our units. I'm going to show you the simplified answer in case those of you at home are wondering what it is. I'm not going to do all this math ahead of time. I'm just going to tell you, sorry, I did the math ahead of time. And I'm going to tell you the answer is 4,535 if you add all those up and do all that. And this is, we need now units. Now as we integrate up, it's going to be then the total number of vehicles, the time that they were in line. So we're going to call that the total time that vehicles were in line. Vehicles, vehicle minutes, I guess we could call it. The total time, the minutes that the vehicles were in line. And that's our answer there for part C. Okay, so we're on to part D now. D is a little bit more of a conceptual understanding here to understand what's going on first. So I'm going to kind of explain some stuff up here, and I've written some stuff up here so that it'll save me time in explaining this video, or this part of the video. So they said during the interval 0 to 90, they want the fewest times that L prime of t equals 0. So let's think about what they're asking and what we have and how to go about proving that or showing the fewest times that's possible. What they've given us is a table of values for L of t. I've taken the time, because I think it's going to help me explain the problem, to graph L of t over here just by plotting the points and connecting it rigidly. Now remember, this is not the actual graph because I'm only using specific data points, and they told me in the beginning of the problem that L of t was twice differentiable, meaning we definitely don't have any corners. But because it's differentiable, then I know that L of t is also going to be continuous, and that's also going to be helpful for me. So I'm going to use this as my basic understanding of the graph, but know that the actual graph could look a little bit different than this. They want the fewest times that L prime of t equals 0. Well, that's L prime, remember, that's the derivative. I mean, think about it this way. The derivative equals 0. That's when the slope equals 0. And the slope equals 0 when we hit like a maximum or a minimum often. Okay. It also it equals 0 at other weird times. But notice they want it the fewest times that it can happen, which means we only need the ones that are guaranteed to happen. Even though this graph could go up and down a bunch in between all these points, we're looking for the fewest number of times that this graph is going to have like a maximum or a minimum essentially on the original graph. That's when the derivative would equal 0. So, looking at this graph, it may be easy for us to identify and kind of pick away like, hey, look, it's going to have one probably here, guaranteed probably here, and probably here. So, we may think, hey, our assumption is going to be 3, which is the correct answer here, but we need to prove why that's true. Okay? First, we need to talk about how do we know from a table of values how to prove that this is a maximum or a minimum. Well, what we have to show is we have to show that the slope between these points is guaranteed positive, and then the slope between these points is guaranteed negative. Okay? The way that we're going to do that is we're going to use the mean value theorem, the MVT. And so now I'm going to uncover kind of what I've been hiding over here, that I've written that L of t is differentiable and L of t is continuous. Those are the prerequisites or the requirements for the mean value theorem. Okay? Remember, the mean value theorem says this, that f prime of c is equal to f of b minus f of a divided by b minus a. Meaning this, that the slope of the tangent line at some point c, where c is between b and a, will equal the slope of the secant line. In other words, if this was our a value here, and let's say, I'm going to erase time for a second, let's put time down here. And this was my, let's use 30 because it's all positive here. This is my b value here. That if I look at these 2 points, and this function is differentiable and continuous, that because this slope here of the secant line, if I use these 2 points, the slope of the secant line would have to be positive. That f of b minus f of a over b minus a would be some positive number. That there must be some point c that exists where the tangent line is also exactly that same slope. This is what the mean value theorem tells us. So because of the mean value theorem, here's what we're allowed to say. Yeah? Because the mean value theorem applies, we can say this, that L prime of t, the derivative, must be positive because this slope is positive between this interval, on the interval 0 to 30. That L prime of t is going to have to be negative, at least at one point, guaranteed, because we're looking for the fewest numbers, guaranteed to be negative between 30 and 45. It's going to be positive again between 45 and 60. On the interval between 45 and 60. And then it's going to be negative on the interval between 60 and 90 because it's going down there all the whole way. On the interval 60 to 90. So at this point now we've used the mean value theorem to tell us, hey, somewhere here the slope is positive, somewhere here the slope's negative, slope's guaranteed to be positive here, and negative at least at one point there. Yeah? That just tells us we're doing this. Okay? But because the original function, they told me L of t was twice differentiable, here's what I now know. I now also know that L prime of t is continuous, because if L prime is differentiable, it must also be continuous. And so because of that, the IVT implies, or the IVT, remember that's the intermediate value theorem, tells us that L prime is going to equal 0 at least 3 times. Let me see if I can explain that second part of it here to you guys. That L prime, if I was to try to graph some version of L prime of t, using this information, I know that L prime is positive between 0 and 30, at least at one spot. It's possible it's also negative, but we're guaranteed it's positive. So if this is 30, I know it's positive here. And then between 30 and 45, I know that at some point here it has to be negative. Okay? between 30 and 45. And then between 45 and 60, it's positive again. And then 60 and 90, I'm guaranteed it's negative. So remember, my question was, what's the fewest number of times L prime of t can equal 0? It's here. These 3 times are the fewest times that it can equal 0. Now, it may not be exactly at those values because we use the MVT to guarantee it happens somewhere in there. But we know that it does happen. And so our answer is that this would happen at least 3 times on the interval 0 to 90. Okay, so we're on to part E. We're on our last part here. Hopefully we're still in good spirits and we're ready to finish out this AP problem. So we're on to part E. On E it says, at t equals 80 minutes, vehicles are joining at a rate of 6 vehicles per minute. So let's stop there and let's see if we can identify what they're telling us, okay? They said at 80 minutes, vehicles join at this rate, okay? So vehicles are coming into the line at this rate. Remember, vehicles in line is this function, and if it's a rate that they're coming in, then it's this the derivative of this function. So essentially they're saying is at 80 minutes, at t equals 80, that L prime, the derivative, at 80 minutes is equal to, they're coming in at this rate, at 6 vehicles per minute. Okay? So this is what they've told me, that L prime of 80 is equal to 6. Essentially they're telling me the rate of change, the exact rate of change here at 80 minutes. Yeah? Now, they said, okay, great. Now that we have that information, now we want to find, here's the goal for E, find the rate of change of wait time at 80 minutes. Now it's looking for the rate of change, that should highlight like derivative or something like that, of the wait time, Now that's going to be this function, so the rate of change of the wait time would be W prime at 80 minutes. Remember, at 80 minutes, that's when L is at 80, okay? So here, then we want to say that we want to find, we know that we're trying to find the rate of change of L of 80. Okay? The wait time when the line has at 80 minutes, okay? The rate of change of this. So we want to take the derivative of this, okay? So the derivative of this would equal, this would make us use the chain rule here. So when we take the derivative of this, we would get the derivative of my outside function, which will be just W prime, times the inside function, which is L of 80, times, when we do chain rule, it's derivative of the outside function, and we write the inside function the same, times the derivative of the inside function, which would be L prime of 80. So, at this point, the brass tacks of the problem are there, and now we're going to be able to just substitute in here. Okay? So, here, because we're looking for this rate, we need to now try to evaluate some of this stuff. Well, that's going to equal W prime of L of 80. L of 80 is going to be the number of vehicles lined at 80 minutes, which is 60, times L prime of 80. Well, L prime of 80, that's what they gave me. Conveniently, notice they gave me information that I'm going to need in this part of the problem. That's not a coincidence. That's they usually will do something like that. So times, this is times L prime of 80 is equal to 6. And we'll put units in a second, but we'll leave it without it there. Now, W prime of 60, this is where a lot of the AP problems are usually pretty infamous at doing this, that they're going to say, hey, go find W prime of 60. Now be careful, we don't want to go back and find the derivative of all this again. We already found the derivative in part B of our problem, and we evaluated that derivative at 60 vehicles in line, and we got pi over 12 vehicles per second for part B. So this is going to be pi over 12 times 6. And now what we need is we need to put our units in here, okay? So our units then, I'm going to erase this pi over 12 here. Our units pi over 12, this was in vehicles per second. Times 6 here was the vehicles per minute. Ooh, this isn't vehicles per second. This was, sorry, I'm going to do an error here. Sorry, from part B, we said this is the wait time, so it was seconds per vehicle. So sorry, this was seconds, the wait time was seconds over vehicle. Times, this was 6 vehicles per minute. And so at this spot here, now we can realize that the vehicles will divide out. And so our units then left over is 6 times pi over 12, which we can write as 6 pi over 12. Or if you want to write it as pi over 2, that's totally fine. And we got 6 pi over 12 seconds per minute. What that's telling us is that our wait time has a rate of change as 6 pi over 12 seconds per every minute. That's how often the wait time is changing there. And you could write that again, if you wanted to, you could write this as just pi over 2, and that would be totally fine too. Notice that you don't have to do that part of it. What they also wanted was the units there. Then after that, we've gotten parts A through E. Hopefully you're able to get this at home, and I hope you guys have a great and wonderful rest of your day.